tonight I have an interesting problem that's going to allow us to use modular arithmetic in a nice way to define an arithmetic progression or an arithmetic sequence. Now, let me just write down what I intended to convey. So, f congruent to t mod d, where ft and d are integers, just means this. The first term, I'm going to call the first term f. Second term would be f plus d. And this is totally in keeping with the definitions of this modular arithmetic definition. Okay, so I'm just writing it out explicitly so you can explicitly see the terms, but you could just say f plus some multiple of d. Right? And I'll go ahead and put in the ubiquitous ellipsis here, and so on. Now, so this is what I intended, but technically speaking, you also have a term directly before this called f minus d. Okay, f minus d would be the term immediately preceding f, right? So in other words, what this defines is all of these terms, okay? All of these terms that you see here with an ellipsis to the left, okay? But I'm just trying to focus on the arithmetic progression starting with the term f, okay? So a little bit loose with the notation, but it gets a point across. Now, I also specified that f and d, f is the first term, d is what they call the common difference. They're coprime, they're relatively prime, they share no prime factors, okay? And what that does for us, when we're trying to show that f squared is a term in the progression, and all we'll have to do is show that f squared is congruent to t, because this is the defining congruence for the arithmetic progression. It's just we're starting at f. Now, famous result right here, the fact that f and d are relatively prime gives us integers x and y such that 1 is equal to a linear combination of f and d, and the letters x and y are kind of famous in this regard. So x and y are just integers. They exist. We don't know what they are, but they do exist by the Euclidian algorithm, where you do the back substitution to get that done. You do long division. You know, it's kind of tedious, but anyway, this is theoretical result that's not hard to prove. Now, so this statement right here can be rewritten like this, but what does this say? That says f times x is 1 plus a multiple of d, right? Well, that's absolutely equivalent to saying f times x is congruent to 1 mod d. And you see that means that we can, since this is a congruence modulo d, and this is a congruence modulo d, we can multiply them together in the same sense that you do with equality, meaning we can multiply fx times f, and that gives us f squared x on the left-hand side. And again, y'all remember, you can multiply equals equals equals. You can do the same thing with congruences. So fx times f certainly gives us f squared x, but the pleasantness of this 1 on the right-hand side gives us it's congruent to 1 times t, which is just t. But remember, this is mod d. I'll abbreviate modulo with mod. So modulo arithmetic is another name for just remainder arithmetic. Okay, so you see that does it. Okay, that means that f of x squared is a term. It's a term in this sequence. F squared x is a term in this sequence for the very same reason f is, right? Okay, so you can think of this as the defining, like if you wanted to put an n up here, n congruent to t means that n is a member of this arithmetic progression. So we've just established what we set out to prove, that a multiple of s squared is a term in the progression or the sequence. Okay. Now let's do a concrete example. We can say QED here. Latin for we have demonstrated. Okay, so QED, and let's just do a concrete example to as sort of a sanity check here. All right, so the one that I dreamed up for you. Let's do 2 is congruent to, does this work out okay? Yeah, 2. We want it to be our first term, so I'm going to do 2 congruent to t. And I'm going to pick something that's going to be relatively prime to, which will be 7. I'm going to do mod 7. Okay, that's an easy, might as well pick a prime, right? So you don't have to, but it's just the numbers it's a little easier to compute. So this defines the sequence. 2 congruent to t. 2 would be the first term in the sequence. 9 would be the second term. In fact, I'll write those down. We have, I'll tell you what, let's switch this off, folks. I have one that's a little bit better. Let's make it, that one works, but this one I'm about to show you is a little nicer. I'd written 2 down and I just got them backwards. Let's try 6 is congruent to t mod 11. Okay, a little more spacing here. Okay, so this literally defines an arithmetic progression beginning at 6, but it does include other terms. But notice I'll just list the elements in the arithmetic progression. We would have 6 as our first term. Now if we add 11 to 6, we get 17, right? That's our second term. If we add 11 to 17, we get 28, our third term. Okay, and you see, what are we looking for? We're looking for a multiple of 6 squared. In other words, we're trying to find a multiple of 6 squared. I'll just write 6 squared times n, right? Because that's what we proved, right? So 28, 39 when you add 11 to 28, 50 when you add 11 to 39. What's next? 61. And you can see it coming up, can't you, ladies and gentlemen? We have 61. If you add 11 to 61, you get 72. But hurrah, because that's 2 times 6 squared, right? 2 times 6 squared, which is exactly the form, our first term squared, multiple, right? So it's a multiple of first term. So it's a lot to write down, but a multiple of the first term squared. Okay, this is a multiple of the first term. I'll just write ft. Squared, right? And y'all, as a lot of you may have surmised, there's nothing sacrosanct about picking the first term. You could pick any term and get the same kind of thing happening, right? It's just a nice kind of reference point. And also, as you may also have deduced, there's nothing that would keep you from saying multiples of the first term cubed if you just kept multiplying this through. Like you could multiply this through f of x congruent to 1, and you would get f cubed x squared is congruent to t also. And again, you could go ad infinitum here. You could get f raised to any power, a multiple of f raised to any power is guaranteed to be a member of this arithmetic sequence. Okay, so I don't know if this is probably not, this is not Olympic level caliber, but it may be lower level competition level, like sophomore, junior in high school. It's not too hard because there's nothing hard about this in terms of it's direct as far as the existence of the integers x and y, and it's just fairly rudimentary modular arithmetic. Okay. But anyway, here's a concrete example of what I was trying to prove. And it kind of cascades. You can get multiple related results based on the idea that was used here. All right, that's all.